Look around you. The world appears solid, tangible, and reassuringly normal. The chair you sit on, the water you drink, the air you breathe, these are the foundations of our reality, the mundane states of matter that build our world. We call them solid, liquid, and gas. And for most of human history, this trinity was thought to be the complete story. But the cosmos, in its calm and silent immensity, is far stranger than we ever imagined. The universe is a vast laboratory where the fundamental laws of physics, under conditions of extreme temperature, pressure, and density, conjure forth states of matter so bizarre they defy our everyday intuition and challenge the very definition of what it means to be. This is a journey into that cosmic laboratory, a story of matter in its most peculiar and wondrous forms. Our exploration begins not on Earth, but in the heart of a star, where matter exists as a superheated electrified fire called plasma, the fourth state and the most common in the universe. From there we will plunge into the opposite extreme, to the chilling stillness of absolute zero, the coldest temperature possible. In this realm of profound cold, the familiar rules of classical physics dissolve, and the weird, ghostly logic of the quantum world takes over. Here, thousands of individual atoms can lose their identity and merge into a single superatom, a Bose-Einstein condensate, that moves and behaves as one coherent wave. We will see how matter, crushed by the immense gravity of dead stars, can become a super-dense solid called degenerate matter, where a teaspoonful would outweigh a mountain. The journey grows stranger still as we venture into the theoretical and the unseen. We will explore the primordial soup of quark-gluon plasma that filled the universe in the first moments after the Big Bang. We will confront the cosmic mysteries of dark matter, the invisible scaffolding upon which galaxies are built, and dark energy, the enigmatic force that is pushing the very fabric of space-time apart. We will witness matter that flows without friction, conducts electricity with perfect efficiency, and even organizes itself into crystals that tick-tock through time itself. This is a story that pushes the boundaries of reality, from matter made of pure light to the theoretical exotic matter that could, in principle, hold open a wormhole. Ultimately, this is a quest to understand our place in the cosmos. The strange states of matter are not just laboratory curiosities. They are the building blocks of the universe. They are the substance of stars, the remnants of cosmic explosions, and the invisible forces that dictate the fate of galaxies. By studying them, we are deciphering the history and future of everything that exists. From the familiar solidity of a rock to the unknowable abyss of a black hole singularity, the story of matter is the story of the universe itself. So let us begin, and in the calm cosmos prepare to discover that the ordinary is merely the beginning. Before we can venture into the bizarre and bewildering landscapes of the quantum world, before we can stand at the edge of a black hole or witness the birth of the universe in a soup of fundamental particles, we must first ground ourselves in the familiar. Our journey into the strange states of matter begins at home, with the classical trinity that defines our physical experience: solid, liquid, and gas. These three states are our cosmic starting point, the fundamental reference against which all strangeness is measured. They may seem ordinary, even mundane, but they are governed by the same universal laws that create the most exotic phenomena in the cosmos. By understanding them on a cosmic scale, we build the foundation for our entire exploration. At its heart, the state of any matter is determined by a simple, elegant duel between two opposing forces: the energy of motion possessed by its constituent atoms or molecules, and the attractive forces that try to bind them together. The outcome of this cosmic tug-of-war dictates whether matter will be a rigid solid, a flowing liquid, or a diffuse gas. The decider in this duel is temperature. Temperature is not some abstract quality. It is a direct measure of the average kinetic energy, the energy of motion, of the particles in a substance. As we add or remove heat, we are directly controlling the vigor of this atomic dance, and in doing so, we are commanding matter to change its state. Let us begin with the state of utmost order, the solid. A solid is matter in which the attractive forces have won a decisive victory. The atoms or molecules have so little kinetic energy that they can no longer roam freely. They are locked into a fixed, rigid structure, a tightly packed lattice where each particle has a designated place. They are not perfectly still. They vibrate in their fixed positions like tiny, tethered bells ringing with thermal energy. but they cannot break free from their neighbours. This is what gives a solid its defining properties, a definite shape and a definite volume. A rock does not change its shape when you move it, because the bonds between its silicon and oxygen atoms are strong, and the atoms themselves are too placid to break them. On a cosmic scale, solids form the very bedrock of our existence. The planet beneath our feet is a colossal sphere of solid rock and metal. The Earth's crust, the continents we live on, are tectonic plates of solid silicate rock floating on a semi-molten mantle. The Moon, Mercury and Mars are solid, cratered worlds. Their surfaces are frozen testament to billions of years of cosmic impacts. In the outer solar system, we find solids of a different kind. The moons of Jupiter and Saturn, like Europa and Enceladus, are covered in a thick crust of water ice, a solid so cold and hard it behaves like rock. Further out in the Kuiper belt lie countless bodies like Pluto, worlds made of exotic frozen solids, nitrogen ice, methane ice and carbon monoxide ice, all locked into a rigid state by the profound cold, hundreds of degrees below zero. These are the building blocks of planets, the solid debris left over from the formation of the solar system, scattered like frozen gravel in the vast dark expanse. The asteroid belt is a river of solid rock and metal, each piece a miniature, irregular world, a testament to the power of cohesive forces to bind matter into a stable, enduring form. Now, let us add energy. As we heat a solid, we increase the vibration of its atoms. They shake more and more violently in their lattice positions, pushing against their neighbours. Eventually they gain enough energy to overcome the rigid bonds that hold them in place. The ordered structure breaks down. The atoms are still attracted to each other, clustering together in a dense crowd, but they are now free to move, to slide past one another. The matter has melted. It has become a liquid. A liquid is the state of compromise. The particles have too much energy to be locked in place, but not enough to escape each other's company entirely. This gives a liquid its unique characteristics. It has a definite volume, but no definite shape. It flows, taking the shape of whatever container it occupies. The molecules in a glass of water are in constant chaotic motion, tumbling over one another, forming and breaking fleeting bonds. This is why a liquid surface is level and why it can form droplets. The cohesive forces are still strong enough to pull the molecules together, minimizing their surface area. In the cosmos, liquids are rarer than solids and gases, as they can only exist within a relatively narrow range of temperatures and pressures. Yet, where they exist, they hold the tantalizing promise of life. Earth is the blue marble, precisely because its surface temperature and pressure allow water to exist in its liquid state, forming the vast oceans that are the cradle of all known biology. But Earth is not alone in hosting cosmic liquids. Scientists now have strong evidence that Jupiter's moon Europa and Saturn's moon Enceladus hide vast global oceans of liquid salt water beneath their icy shells. Warmed by the tidal forces of their giant parent planets, these dark subterranean oceans are considered among the most promising places to search for extraterrestrial life in our solar system. The liquids of the cosmos are not limited to water. On Saturn's largest moon, Titan, the temperature is a frigid minus 179 degrees Celsius, minus 290 degrees Fahrenheit. At this extreme cold, water is as hard as granite, but methane and ethane, which are gases on Earth, condense into liquids. The Cassini spacecraft revealed a stunning landscape on Titan, a world eerily similar to Earth, but built from a completely different chemistry. It has rivers, lakes, and even seas, not of water, but of liquid natural gas. It rains liquid methane from its orange, nitrogen-rich sky, carving river channels into the frozen water ice bedrock before pooling in vast dark basins like Kraken Mare, a sea larger than all of North America's Great Lakes combined. Even deeper inside planets, strange liquids exist. The churning liquid iron outer core of the Earth generates our planet's protective magnetic field. Deeper still, inside gas giants like Jupiter and Saturn, the immense pressure is thought to squeeze hydrogen into a bizarre liquid metallic state. Let us continue to add energy. If we heat a liquid, its molecules move faster and faster. The chaotic dance becomes a frenzy. Eventually the particles gain so much kinetic energy that they completely overcome the attractive forces holding them together. They break free from the collective and fly off in all directions, moving randomly and at high speed. The matter has vaporized. It has become a gas. A gas is the state of ultimate freedom and disorder. The particles are far apart and interact only weakly, colliding and bouncing off each other like billiard balls. A gas has neither a definite shape nor a definite volume. It will expand to fill any container it is placed in, no matter how large. The air we breathe is a gas, a mixture of nitrogen, oxygen, and other molecules, all moving at hundreds of miles per hour. Their random collisions creating the atmospheric pressure that is essential for our survival. On a cosmic scale, gas is king. The universe is overwhelmingly composed of gas. The vast, seemingly empty spaces between the stars are not truly empty. They are filled with the interstellar medium, a diffuse, tenuous gas made mostly of hydrogen and helium. While the density is incredibly low, sometimes only a few atoms per cubic centimetre, the sheer volume of space means that this gas constitutes a huge amount of the universe's ordinary matter. It is from this gas that new stars are born. Under the influence of gravity, a cloud of interstellar gas can begin to collapse in on itself. As it collapses, it fragments into smaller, denser clumps called protostars. The pressure and temperature at the core of a protostar rise dramatically. Our own sun and every star you see in the night sky was born from such a cloud. The stars themselves are colossal spheres of hot gas. The planets we call gas giants, Jupiter, Saturn, Uranus, and Neptune, are worlds defined by their gaseous nature. They are composed almost entirely of hydrogen, helium, and methane gas, forming deep, turbulent atmospheres thousands of miles thick. Their surfaces are not solid. They are simply the level at which the atmospheric pressure equals that of Earth at sea level. To descend into Jupiter would be a journey through ever denser layers of gas, crushed by unimaginable pressure, with no solid ground to ever stand on. The beautiful coloured bands and swirling storms like the Great Red Spot are all weather patterns in this planet-sized ocean of gas. The nebulae, some of the most beautiful objects in the cosmos, are vast, glowing clouds of gas and dust, stellar nurseries, where new stars are being forged, or the funeral shrouds of stars that have died. The Orion Nebula, for example, is a brilliant stellar nursery, a chaotic and beautiful region where the intense radiation from newborn stars is causing the surrounding gas to glow, painting a masterpiece across the heavens. Thus, the three classical states, solid, liquid, and gas, are not just earthly phenomena. They are cosmic archetypes. They describe the rock of a dead world, the methane sea of an alien moon, and the hydrogen atmosphere of a giant planet. They are the result of the universal battle between atomic motion and intermolecular attraction, a battle refereed by temperature. Understanding this fundamental dance of particles is the essential first step. It provides us with the language and the concepts we need to describe the universe we can see. But this is only the beginning, for when we push the conditions of temperature and pressure to extremes far beyond our everyday experience, this simple trinity of states breaks down, and matter begins to reveal its truly strange and wonderful nature. The next step on our journey takes us into the fire of the stars to meet the fourth and most common state of all. We have established our foundation in the familiar world of solids, liquids, and gases, the three states of matter governed by the interplay of atomic motion and attraction. In this classical framework, atoms are the fundamental, unbreakable units, behaving like tiny billiard balls that can be locked in a lattice, slide past one another, or fly freely. But what happens if we continue to add energy? What happens when the atomic dance becomes so violent that the atoms themselves can no longer hold together? The answer to this question takes us beyond the classical trinity and into the realm of the fourth state of matter, plasma. It is a state of matter that is relatively rare on Earth's surface, yet it is, by a staggering margin, the most common state of ordinary matter in the entire universe. To understand plasma is to understand the fire of the stars, the substance of nebulae, and the very engine of the cosmos. The transition to plasma is the most dramatic state change yet. Imagine a gas, its atoms already flying freely in a state of chaotic motion. Now, we heat this gas to extreme temperatures, thousands or even millions of degrees Celsius. At these incredible energies, the collisions between the gas atoms become spectacularly violent. They are no longer gentle bounces but cataclysmic impacts. In these collisions, the kinetic energy is so high that it can overcome the fundamental electromagnetic force that binds electrons in their orbits around the atomic nucleus. an electron is knocked clean off its parent atom. The result is a profound transformation of the substance. The once neutral atom is now split into two distinct entities, a negatively charged free electron and a positively charged ion, the original atom now missing an electron. When this process, called ionization, happens to a significant fraction of the atoms in a gas, it ceases to be a gas and becomes a plasma. A plasma is often defined as an ionized gas, but this simple definition belies its true complexity. It is not just a hot gas. It is a fundamentally new state of matter with its own unique and extraordinary properties. The key difference between a gas and a plasma is that a plasma is electrically active. A gas is composed of neutral atoms, which are largely indifferent to electric and magnetic fields. A plasma, on a cosmic scale, is a roiling soup of charged particles, a sea of free electrons and positive ions. This single fact changes everything. Because its constituents are charged, a plasma can conduct electricity. More importantly, it can be powerfully influenced by, and can itself generate magnetic fields. This introduces a whole new set of forces into the cosmic tug-of-war. While the behavior of a gas is governed primarily by pressure and temperature, the behavior of a plasma is dominated by the complex and often counterintuitive laws of electromagnetism. On Earth, we encounter plasma in fleeting, spectacular forms. The jagged, brilliant flash of a lightning bolt is a channel of air that has been superheated by an electrical discharge into a temporary plasma state. The gentle, ethereal glow of the aurora borealis and aurora australis is another example. These celestial light shows are created when charged particles from the sun, the solar wind, are funneled by the Earth's magnetic field toward the poles, where they collide with atoms in the upper atmosphere, stripping their electrons and causing them to glow. Even the mundane fluorescent light bulb in an office contains a low-pressure mercury plasma. An electric current passed through the tube energizes the mercury vapor, which then emits ultraviolet light that causes the tube's phosphor coating to glow with visible light. The neon sign, the plasma TV screen, these are all small, contain pockets of the fourth state. But to truly appreciate plasma, we must look to the cosmos, for the universe is overwhelmingly made of it. An estimated 99.9% of all visible matter exists in the plasma state. Every star you see in the night sky, including our own sun, is a colossal sphere of plasma. The sun is not a ball of burning gas, as it is sometimes described in a poetic but inaccurate sense. Burning is a chemical reaction. The sun is a site of nuclear fusion. At its core, the temperature and pressure are so immense, around 15 million degrees Celsius, that hydrogen nuclei are fused together to form helium, releasing an incredible amount of energy in the process. This energy radiates outward, keeping the entire star superheated and ensuring that its substance remains a dense, roiling plasma. The surface of the sun, the photosphere, is a cooler, but still blistering, 5,500 degrees Celsius. Here we can see the plasma in action. The granulated patterns on the sun's surface are the tops of convection cells, columns of hot plasma rising from the interior, cooling and sinking back down. Sunspots, the dark blemishes on the solar surface, are regions of intense magnetic activity, where the magnetic field lines are so strong that they inhibit convection, creating cooler, darker patches of plasma. The most spectacular displays of solar plasma are solar flares and coronal mass ejections, CMES. These are colossal eruptions where the sun's tangled magnetic field lines suddenly snap and reconfigure, launching billions of tons of plasma out into space at millions of miles per hour. Our molecule, if it were part of the sun, would be caught in this chaotic magnetized dance, a charged particle swept along by forces of unimaginable scale. The sun's influence doesn't end at its visible surface. It constantly boils off a stream of plasma from its outer atmosphere, the corona. This stream is the solar wind, a continuous outflow of electrons and protons that flows outward through the entire solar system. It is a tenuous plasma, but it shapes the space around us. It is the solar wind that creates the auroras on Earth and other planets, and it is the pressure of this wind that pushes on the material evaporating from a comet, forming its long, straight ion tail, which always points directly away from the sun. Our entire solar system is embedded within the sun's plasma atmosphere, Beyond the Sun, the universe is awash with plasma. The vast, seemingly empty spaces between the stars, the interstellar medium, are not just filled with neutral gas, they're also permeated by regions of plasma. The most beautiful objects in the night sky, the emission nebulae like the Orion Nebula or the Lagoon Nebula, are stellar nurseries. They are vast clouds of gas and dust where new stars have recently been born. The intense ultraviolet radiation from these hot young stars ionizes the surrounding gas, causing it to glow in vibrant shades of red, pink, and blue. The nebula is, in effect, a cosmic-scale fluorescent lamp, with the newborn stars providing the energy. The beautiful colours come from the specific spectral lines of the ionized elements, the deep red from hydrogen, the blues and greens from oxygen. When massive stars die, they do so in a cataclysmic explosion called a supernova. For a brief period, a single supernova can outshine its entire host galaxy. This explosion blasts the star's material, a rich brew of heavy elements forged in its core, out into space at incredible speeds. This ejected material forms a supernova remnant, a beautiful expanding shell of superheated plasma. The Crab Nebula is a famous example, the remnant of a supernova that was observed by Chinese astronomers in the year 1054. Today, nearly 1,000 years later, we can still see the intricate filamentary structure of the expanding plasma cloud, energized by the rapidly spinning neutron star left behind at its center. Even entire galaxies are held within halos of hot, diffuse plasma. Clusters of galaxies, the largest gravitationally bound structures in the universe, are filled with the intracluster medium, a vast reservoir of extremely hot, tens of millions of degrees, but very low-density plasma, visible only through X-ray telescopes. Because plasma is composed of charged particles that are governed by electromagnetism, it can exhibit complex collective behavior that is impossible in a neutral gas. Waves, instabilities, and self-organizing structures can emerge. Plasma can form filaments, sheets, and jets. For example, astronomers observe colossal jets of plasma being fired out from the regions around supermassive black holes at the centers of active galaxies. These jets, powered by the accretion of matter onto the black hole, can be larger than the galaxy itself, traveling at near the speed of light and glowing brightly in radio wavelengths. They are a stunning demonstration of how magnetic fields can collimate and accelerate plasma on a galactic scale. The study of plasma, therefore, is crucial to understanding the cosmos. It is the key to understanding how stars are born, how they live, and how they die. It explains the structure of nebulae, the power of supernovae, and the dynamics of galaxies. The universe is not just a collection of inert objects moving under the influence of gravity. It is an electrically active dynamic environment, threaded with magnetic fields and filled with the roiling, energetic fire of plasma. Our journey into the strange states of matter has now taken its first major step beyond the familiar. We have superheated a gas to the point where its atoms have been torn apart, creating a substance that is not just hot, but electrically alive. We have found this substance everywhere in the cosmos, from the heart of our sun to the most distant galaxies. We have seen that the universe is not a cold, dark place punctuated by points of light, but a cosmos filled with and shaped by this fourth, fiery state. But the journey is far from over. Having explored the realm of extreme heat, we must now turn to the opposite end of the spectrum. Our next destination is the realm of extreme cold, a place where the frantic dance of atoms slows to an almost complete standstill, and where matter begins to obey the even stranger rules of the quantum world. Our journey so far has taken us from the familiar solids, liquids, and gases of our world to the stellar fire of plasma, the universe's most abundant state of matter. We have explained these states through a classical lens, imagining atoms as tiny billiard balls, whose energy of motion battles against their mutual attraction. This model works beautifully for the high-energy world of plasma and the familiar states of our daily lives. But to venture further, to explore the truly strange states of matter that await us in the cosmos, this classical intuition is no longer enough. We must now take a detour, a plunge into a realm so counterintuitive, so contrary to our everyday experience, that it can feel like entering another reality. We must take the quantum leap. This chapter is our guide to the bizarre and wonderful rules of the very small, the principles of quantum mechanics that govern the universe on its most fundamental level. Without this guide, the strange lands ahead would be incomprehensible. The story of quantum mechanics begins with a crisis in physics at the end of the 19th century. Classical physics, the laws laid down by Isaac Newton and James Clerk Maxwell, had been spectacularly successful. They could predict the orbits of planets, the behaviour of electricity and magnetism, and the mechanics of machines. But when physicists tried to use these laws to explain certain phenomena at the atomic scale, they failed spectacularly. One such failure was the ultraviolet catastrophe. Classical theories predicted that a hot object should radiate an infinite amount of energy in the form of high-frequency light, like ultraviolet rays. This was obviously wrong. A hot poker glows red. It doesn't instantly vaporize you with a blast of infinite energy. The solution came in 1900 from a German physicist named Max Planck. He proposed a radical idea. Energy, he suggested, is not continuous. It can only be emitted or absorbed in discrete tiny packets, which he called quanta, from the Latin for how much. It was like saying you can't pour water in a continuous stream, but only in individual identical droplets. According to Planck, the energy of a single quantum was directly proportional to the frequency of the radiation. This simple but revolutionary idea solved the ultraviolet catastrophe, but it opened the door to a whole new way of thinking about the universe. Energy wasn't smooth, it was chunky. This idea of quantization, the chunkiness of nature, is the first and most fundamental rule of the quantum world. Just as matter is made of discrete atoms, energy is made of discrete quanta. This principle extends to everything at the atomic scale. An electron orbiting an atomic nucleus, for instance, cannot have just any old energy. It is restricted to a specific set of discrete energy levels, like a person standing on a ladder who can only be on the rungs and never in between them. To move from one level to another, an electron must absorb or emit a precise quantum of energy, often in the form of a photon, a quantum of light. This is why elements emit light at specific characteristic frequencies when heated. We are seeing the electrons jumping down the rungs of their energy ladders and releasing photons with specific energies, creating a unique spectral fingerprint for each element. The second bizarre rule of the quantum world is wave-particle duality. In our classical world, things are either particles, localized objects like a baseball, or waves, spread out disturbances like a ripple on a pond. In the quantum realm, this distinction dissolves. A quantum object, like an electron or a photon, behaves as both a particle and a wave, depending on how you observe it. If you shoot an electron at a screen, it will arrive as a single, localized particle, making a tiny dot. But if you shoot many electrons through a barrier with two slits in it, they will create an interference pattern on the screen behind it, a pattern of alternating light and dark bands that can only be explained if each electron passed through both slits at once, like a wave, and interfered with itself. This is profoundly strange. It's like throwing a baseball at a wall with two windows and having it somehow go through both windows simultaneously. The quantum wave is not a physical wave, but a wave of probability. It is called the wave function, and it describes the likelihood of finding the particle at any given point in space. The particle doesn't have a definite position until you measure it. Before the measurement, it exists in a superposition of all possible states, a ghostly smear of potentiality described by its wave function. The act of observation forces the particle to choose a single state, a single location. This idea, that reality at its most fundamental level is probabilistic and is affected by the act of observation, is one of the most challenging but essential concepts in all of science. This wave-like nature of matter has a crucial consequence. The larger a particle's momentum, the shorter its wavelength. Heavy, fast-moving objects like a baseball have a wavelength so infinitesimally small that it's completely undetectable. But for a tiny, slow-moving particle like an electron, the wavelength can be significant, even larger than the atom itself. As we will see, when we cool matter down to near absolute zero, the particles slow down so much that their quantum wavelengths grow enormous, leading to truly bizarre collective behaviours. The third and final quantum rule we need is the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. This principle governs the behaviour of a large and important class of particles called fermions. Fermions are the particles that make up all the matter we see around us. Electrons, protons and neutrons are all fermions. The Pauli exclusion principle states a simple but powerful rule. No two identical fermions can occupy the same quantum state in the same place at the same time. Think back to the ladder of energy levels in an atom. Each rung on the ladder is a quantum state defined by its energy, momentum, and another quantum property called spin. The exclusion principle is like a cosmic rule of social distancing for fermions. It says that each quantum state can only hold one fermion. If a state is already occupied by an electron, no other electron can enter that state. It is excluded. This principle is the foundation of all chemistry. It explains why atoms have a structure, with electrons filling up the available energy levels in shells from the lowest energy state upwards. Without the exclusion principle, all the electrons in an atom would collapse into the lowest energy state, and the rich, complex structure of the periodic table, and therefore all of chemistry and life, would not exist. The chair you're sitting on is solid because the electrons in its atoms are obeying the Pauli exclusion principle, refusing to be in the same state, and thus creating the structure and volume of matter. The universe, however, also contains another class of particles called bosons. Photons, particles of light, and certain atoms, those with an even number of fermions, are bosons. Bosons are the social butterflies of the quantum world. They are not subject to the Pauli exclusion principle. An unlimited number of identical bosons can occupy the exact same quantum state at the same time. They are happy to pile up on the same energy rung of the ladder. This fundamental difference in behavior between fermions, which are solitary, and bosons, which are gregarious, is the key to understanding the next two strange states of matter on our journey. So, let us summarize our quantum toolkit. First, energy and other properties are quantized. They exist in discrete packets or levels. Second, all matter exhibits wave-particle duality, its state described by a wave function of probability until it is measured. Third, matter particles, fermions, are antisocial and obey the Pauli exclusion principle, refusing to share a quantum state. In contrast, force-carrying particles and some atoms, bosons, are social and love to share a quantum state. These rules may seem abstract, but they are the operating system of the universe. They are not just theoretical curiosities, they have tangible, large-scale consequences. The stability of the sun, the solidity of the earth, and the very existence of chemical bonds are all direct results of these quantum laws. Our journey into strange matter is now poised to begin in earnest. We are leaving the classical world behind, armed with these new, strange rules. We will see what happens when we cool a gas of boson atoms so cold that their quantum wavelengths overlap, and they decide to collapse into a single, unified quantum state. We will see what happens when we crush a star so dense that its fermion particles are forced into higher and higher energy states, creating a degeneracy pressure that can hold back the force of gravity itself. The quantum leap is not just a leap in understanding, it is a leap into a new reality, a reality where matter can become a single superatom, where stars can become city-sized diamonds, and where the fundamental nature of space and time can be bent and broken. The rules are set. The journey can now continue into the chilling depths of absolute zero. Having armed ourselves with the strange and powerful rules of quantum mechanics, we are now ready to explore the first of the truly exotic realms of matter. Our path takes us away from the unimaginable heat of the stars, and toward its opposite, the unimaginable cold of absolute zero. This is not merely a journey to a very cold place, it is a journey to a state of profound stillness, a place where the classical world of thermal motion fades away and the ghostly, underlying quantum nature of reality is laid bare. Absolute zero is the gateway to the stranger states of matter, the ground floor of the quantum world, where the universe reveals its most fundamental and coherent self. What is temperature? As we've discussed, it is a measure of the average kinetic energy of the particles in a substance. The atoms in a hot gas fly about frantically. The atoms in a cooler solid vibrate in place. As we cool a substance, we are systematically removing this energy of motion, calming the atomic dance. The concept of absolute zero arises from a simple question. What happens when you remove all the thermal energy you possibly can? Is there a point where the particles become completely, perfectly still? This point is absolute zero. It is defined as 0 Kelvin on the Kelvin scale, which is equivalent to minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. It is the theoretical lowest possible temperature, the point at which all classical motion ceases. It is the ultimate state of cold. It's important to note that, due to the laws of thermodynamics and the quantum uncertainty principle, it is physically impossible to ever actually reach absolute zero. We can get incredibly close. Scientists in laboratories have achieved temperatures of just a few billionths of a degree above absolute zero, but we can never get all the way there. It is an asymptotic limit, a destination we can approach but never arrive at. However, as we get tantalizingly close to this ultimate cold, the world changes completely. In our everyday experience, the quantum nature of matter is hidden. The thermal energy of particles is so high that they are constantly jiggling and jostling, a phenomenon known as thermal noise. This random motion washes out the subtle, coherent effects of the quantum world. It's like trying to hear a faint, pure musical note in the middle of a roaring crowd. The quantum signal is there, but it's drowned out by the classical noise. Cooling a substance to near absolute zero is like silencing the crowd. As the thermal noise dies down, the underlying quantum music begins to emerge. The wave-like nature of particles, once a subtle and abstract concept, becomes a dominant feature of reality. Recall that a particle's quantum wavelength, its de Broglie wavelength, gets larger as its momentum gets smaller. As we cool a particle down, we slow it down, reducing its momentum and therefore causing its wave function, its cloud of probability, to spread out and grow larger. At room temperature, the wavelength of an atom is minuscule, far smaller than the atom itself. The atoms are like tiny distinct billiard balls, with vast empty spaces between them, but as we approach absolute zero, the wavelength of each atom begins to grow. It can become larger than the atom itself. As the cooling continues, the wavelengths continue to expand until a critical point is reached. The wave functions of neighbouring atoms start to overlap. This is the moment when everything changes. The atoms are no longer distinct separate entities. They can no longer be thought of as individual billiard balls. Their quantum identities, their clouds of probability, have merged. They have entered a state of quantum coherence, where they begin to lose their individuality and start to behave as a single collective entity. It's as if the crowd, having fallen silent, now begins to sing in perfect harmonious unison. The system is no longer a collection of individual particles. It is a macroscopic quantum object, an object where the bizarre rules of the quantum world are no longer confined to the scale of a single atom, but are now manifested on a scale we can observe and measure. This transition into a coherent quantum state is the key to all the ultra-cold states of matter we are about to explore. The specific nature of this state, however, depends critically on whether the particles involved are bosons or fermions. Let's first consider a gas of boson atoms. As we learned, bosons are social particles. They are perfectly happy to occupy the same quantum state. As we cool the gas of bosons and their wave functions begin to overlap, something remarkable happens. The bosons begin to condense into the single, lowest possible energy state available to them. It's not a condensation in physical space, like water vapor condensing into a liquid droplet. It is a condensation in momentum space. One by one, the atoms abandon their higher energy states and fall into the ground state, the lowest rung on the quantum ladder. Past a certain critical temperature, a large fraction of the atoms in the gas will all be occupying this single quantum state. They have all merged into a single, massive wave function. They have lost their individual identities and are now completely indistinguishable, behaving as a single superatom. This is the fifth state of matter, the Bose-Einstein condensate, a coherent cloud of matter that is our next major topic. The journey to absolute zero is what makes this state possible, by allowing the quantum natures of the atoms to overlap and merge. Now, let's consider a gas of fermion atoms. Fermions, as we know, are antisocial. They are governed by the Pauli exclusion principle, which forbids any two of them from occupying the same quantum state. So, what happens when we cool a gas of fermions? They cannot all simply collapse into the lowest energy ground state, because once that state is occupied by one fermion, it is full. Instead, as we cool the gas, the fermions begin to fill up the available energy states, starting from the bottom. The first fermion goes into the ground state, the second goes into the next lowest energy state, and so on. Even as we approach absolute zero, when there's almost no thermal energy left, the fermions are forced to occupy a wide range of energy states. The highest energy level occupied at absolute zero is called the Fermi energy, and the collection of filled energy states is called the Fermi sea. This is a purely quantum mechanical effect. The particles have kinetic energy not because they are hot, but because the exclusion principle forces them into higher energy rungs. This creates a powerful outward pressure, known as degeneracy pressure, which can resist immense gravitational forces. This is the state of degenerate matter, the substance that makes up white dwarf and neutron stars, and it is a direct consequence of cooling fermions in the absence of thermal noise. The realm of absolute zero is therefore the gateway to these two great families of quantum matter. It is the place where the fundamental distinction between bosons and fermions becomes a macroscopic reality. It is the place where matter can either unify into a single coherent whole, or organize itself into a rigid hierarchy of energy levels. Furthermore, it is in this ultra-cold realm that other strange quantum phenomena can emerge. Superconductivity, the ability of a material to conduct electricity with zero resistance, and superfluidity, the ability of a fluid to flow with zero viscosity, are both low-temperature phenomena that arise from the quantum coherence of particles. In a superconductor, electrons, which are fermions, find a way to pair up, and these pairs act like bosons, allowing them to condense into a coherent state that can flow without resistance. In a superfluid, like liquid helium-4, whose atoms are bosons, the atoms condense into a single quantum state, allowing the entire fluid to flow as one coherent wave without any internal friction, enabling it to do bizarre things like climb up the walls of its container. The journey toward absolute zero is therefore a journey of revelation. It is a process of stripping away the chaotic thermal mask of the classical world to reveal the pure, coherent, and beautifully strange quantum reality that lies beneath. It is the ultimate demonstration that the universe is, at its foundation, a quantum entity. The cold does not just slow things down, it allows them to unify, to organize, and to manifest the fundamental rules of their existence on a scale we can witness. We are now standing at the threshold of this new world. The crowd is silent. The stage is set. It is time to meet the first of these strange new actors, the superatom known as the Bose-Einstein condensate. Our journey has led us to the precipice of the quantum world. We have navigated the bizarre rules of the very small and journeyed to the profound stillness of absolute zero, where the chaotic noise of thermal energy fades to a whisper. It is here, in this realm of extreme cold, that matter sheds its classical disguise and reveals its true quantum nature. We saw. This revelation depends critically on the type of particle involved, the solitary fermion or the gregarious boson. Now, we will witness the extraordinary consequences of the boson's social nature. We are about to meet the fifth state of matter, a state predicted by Albert Einstein nearly a century ago, but only created in a lab in 1995. It is a state of matter so strange, so unified, that it challenges our very concept of individuality. This is the Bose-Einstein condensate, the superatom. The story begins in the 1920s, not in a laboratory, but on paper, in the minds of two of the 20th century's greatest physicists. An Indian physicist named Satyendra Nath Bose developed a new way to describe the statistical behavior of photons, the quantum particles of light. He treated them not as distinguishable particles, but as fundamentally indistinguishable entities. He sent his work to Albert Einstein, who was immediately struck by its profound implications. Einstein realized that this new statistical method, now called Bose-Einstein statistics, could be applied not just to photons, but to any particle that was a boson. Einstein took the idea one step further. He applied the statistics to a gas of boson atoms and made a startling prediction. He calculated that if you could cool such a gas down below a certain critical temperature, something utterly unprecedented would happen. The atoms would not simply slow down, they would undergo a quantum phase transition. They would begin to abandon their individual higher energy quantum states and condense into the single, lowest possible energy state available to the system. Einstein predicted that, below this temperature, a significant fraction of the atoms would cease to exist as individual particles and would merge into a single quantum entity, a new state of matter. For 70 years, this prediction remained a theoretical curiosity, a ghost in the mathematical machine of quantum mechanics. The technological challenge of cooling a gas of atoms to the incredibly low temperatures required, mere millionths or even billionths of a degree above absolute zero, seemed insurmountable. Then, in 1995, at a laboratory in Boulder, Colorado, two physicists, Eric Cornell and Carl Wyman, finally achieved the impossible. Using a sophisticated combination of laser cooling and magnetic trapping, they took a cloud of rubidium atoms, which are bosons, and cooled them down to less than 170 nanokelvin, 170 billionths of a degree above absolute zero. At this unfathomably cold temperature, they watched as the atoms did exactly what Einstein had predicted. The atoms, which had been behaving like a diffuse gas cloud, suddenly collapsed into a dense, compact core at the center of their magnetic trap. This core was not a solid or a liquid. The atoms within it were not separate entities. Their quantum wave functions, which had grown enormous in the extreme cold, had overlapped and merged into one. They had created the world's first Bose-Einstein condensate BEC. To understand what a BEC is, we must fully embrace the wave-particle duality of matter. Every atom is also a wave. At room temperature, the wavelength of an atom is tiny, and the atoms are like a crowd of people, each person a distinct individual. As you cool the atoms, their wavelengths grow. It's as if each person in the crowd begins to get fuzzy and spread out. As you approach the critical temperature for condensation, the fuzziness of each atom wave becomes so large that it starts to overlap with its neighbours. At the moment of condensation, the boundaries between the individual atom waves dissolve completely. The entire collection of atoms begins to behave as a single massive matter wave. The crowd has ceased to be a collection of people and has become a single unified entity. This is the essence of a BEC. It is a macroscopic quantum object. The weirdness of the quantum world, usually confined to the subatomic scale, is suddenly manifested on a scale large enough to be seen with the right equipment. The condensate can contain thousands or even millions of atoms, but it's described by a single wave function, just as if it were a single particle. It has a single quantum identity. The atoms within it are not just identical, they are truly indistinguishable. They have lost their individuality and become part of a coherent whole. This is why it's often called a superatom. The properties of a BEC are, as one might expect, deeply strange. Because it is a single, coherent matter wave, it exhibits wave-like behaviours on a macroscopic scale. For example, if you create two separate BECs and allow them to expand and overlap, they will create an interference pattern just like two overlapping water waves or two beams of laser light. You see alternating bands where the matter waves have constructively interfered, peaks adding to peaks, and destructively interfered, peaks cancelling out troughs. This is a stunning demonstration of the BEC's nature. You're seeing an interference pattern made not of light, but of matter itself, a direct visualization of the wave-like nature of thousands of atoms acting in perfect unison. Another bizarre property is superfluidity. A Beck, being a coherent quantum state, can flow without any viscosity or internal friction. If you were to stir a BEC in a tiny magnetic bowl, it would in principle continue to swirl forever, as there is no way for the collective motion to dissipate as heat. The atoms are all locked into a single quantum state, and there are no lower energy states for them to fall into to create friction. This is related to the superfluid seen in liquid helium, but a BEC is in some ways a purer, more fundamental example, as it is a dilute gas where the interactions between atoms are much weaker and easier to model. The creation of a Beck in the lab was a triumph of experimental physics, earning Cornell, Wieman and Wolfgang Ketteler, who achieved a Beck, shortly after at MIT the 2001 Nobel Prize in Physics. It opened up a whole new field of research, allowing physicists to study and manipulate a macroscopic quantum object with unprecedented control. They can poke it, stir it, and shine lasers at it to see how this strange new substance responds. It has become a quantum simulator, a controllable system that can be used to model other, more complex quantum systems that are difficult to study directly, such as the behavior of electrons in a superconductor or even the conditions in the early universe. One of the most exciting applications is in the field of atom optics. Just as conventional optics uses lenses and mirrors to control beams of light, photons, atom optics aims to do the same with beams of atoms. A BEC can be used to create an atom laser. Unlike a flashlight, which spews out atoms randomly like a gas, an atom laser emits a continuous, coherent beam of atoms, all in the same quantum state, all moving in the same direction. It is a beam of matter that behaves like a beam of laser light. Such a tool has the potential to revolutionize precision measurement, allowing for the creation of incredibly sensitive atomic clocks, rotation sensors, and gravimeters. It could be used for atom lithography, to write incredibly small precise circuits on a silicon chip, atom by atom. While BECs were first created in Earthbound labs, their study has now moved into space. The Cold Atom Laboratory, CAL, on the International Space Station is a facility designed to create and study BECs in a microgravity environment. On Earth, gravity is a constant nuisance for these experiments. The Beck is a delicate, fragile state, and it is constantly being pulled downward by gravity, limiting the amount of time it can be observed before it falls out of the magnetic trap. In the freefall environment of the ISS, a BEC can be observed for much longer periods, up to 10 seconds or more. This allows for more precise measurements and enables experiments that are simply not possible on the ground. It also allows scientists to create BECs at even colder temperatures, as they don't need as strong a magnetic trap to counteract gravity, pushing ever closer to the absolute limit of zero. Does the Bose-Einstein condensate exist naturally in the cosmos? This is a more speculative question. The conditions required, extremely low temperatures and relatively high densities, are hard to find. However, some theorists have proposed that certain types of hypothetical particles, such as axions, which are a candidate for dark matter, could form a cosmic-scale BEC. If this were the case, the entire dark matter halo of a galaxy could be a single, coherent quantum object. Other theories suggest that states analogous to BECs could form in the ultra-dense cores of neutron stars, involving particles called pions or kaons. For now, however, the BEC remains primarily a creature of the laboratory, a state of matter that we have coaxed into existence by pushing technology to its absolute limits. The Bose-Einstein condensate represents a profound milestone in our journey. It is the ultimate expression of quantum coherence, the point where the distinction between the microscopic and the macroscopic dissolves. It is a state of matter where thousands of atoms conspire to act as one, where matter can be made to behave like light, and where the fundamental wave-like nature of reality is made manifest. It is a testament to the predictive power of quantum theory and the ingenuity of experimental science. We have taken a gas of ordinary atoms and, by draining away their thermal energy, have revealed the extraordinary, unified quantum soul that lay dormant within. We have seen what happens when the social bosons are allowed to indulge their gregarious nature to the ultimate degree. Now we must turn our attention to their antisocial cousins, the fermions, and see what strange state of matter they create when subjected to the same cosmic pressures. We have just witnessed the extraordinary spectacle of the Bose-Einstein condensate, a state of matter where social boson particles, chilled to near absolute zero, abandon their individuality and merge into a single coherent quantum entity. It is a state of ultimate unity. Now, we must turn our attention to the other half of the quantum world, to the particles that form the very substance of our reality, the fermions. Electrons, protons, and neutrons, the building blocks of atoms, are all fermions. And fermions, as we know, are governed by a strict and inviolable rule, the Pauli exclusion principle. They are the ultimate individualists, refusing to share their quantum state with any other identical fermion. This fundamental antisocial nature means that when a collection of fermions is cooled and compressed, it cannot simply collapse into a single ground state like bosons do. Instead, it is forced into a strange and powerful configuration known as degenerate matter. This state is the fermionic counterpart to the BEC, but its properties are dramatically different. It is not a state of quiet coherence, but one of ferocious, pent-up energy. Degenerate matter is the silent powerhouse of the cosmos, the substance that holds dead stars up against the crushing force of gravity, and its existence is a direct and spectacular consequence of the quantum rules of exclusion. To understand degenerate matter, let us imagine taking a gas of fermions, for instance, electrons, and placing them in a box. Now, we begin to cool the gas and simultaneously shrink the box, compressing the electrons into a smaller and smaller volume. As we cool the gas, we are removing its thermal energy. In a classical gas, this would mean the pressure drops. But for fermions, something else happens. The Pauli exclusion principle acts like a cosmic housing regulation. Each quantum state, defined by its energy, momentum, and spin, is a house that can only hold one electron. As we cool and compress the gas, the electrons must find a place to live. The first electron settles into the lowest energy state, the ground state. The second electron can't join it, so it must occupy the next lowest energy state. The third fills the next one, and so on. The electrons are forced to build a tower of energy states, filling them up from the bottom one by one. This tower of occupied states is called the Fermi sea. Even as we approach absolute zero and all the thermal energy is gone, the electrons are not all at rest. Most of them are in highly energetic states. Their kinetic energy a direct result not of heat, but of quantum necessity. The energy of the highest occupied state at absolute zero is a crucial benchmark known as the Fermi energy. This is the essence of a degenerate state. The quantum states below the Fermi energy are almost completely filled, and the states above it are almost completely empty. The particles are locked into this configuration by the exclusion principle. Now, consider what happens if we try to compress this matter further. To squeeze the electrons closer together, we would have to force them into quantum states that are already occupied. But the exclusion principle forbids this. The only way to compress the matter is to provide enough energy to push an electron into a much higher, unoccupied energy state, above the Fermi sea. This requires a tremendous amount of energy. The result is that the matter resists compression with an immense force. This resistance is not due to thermal motion or electrostatic repulsion between the electrons. It is a purely quantum mechanical pressure, born from the Pauli exclusion principle. It is called degeneracy pressure. It is an incredibly powerful and stubborn force, far stronger than any classical pressure at high densities. It is the pressure that arises from fermions refusing to be in the same place at the same time with the same energy. A good analogy is a multi-story parking garage. Each parking spot is a quantum state. If you have 100 cars, fermions, you can't park them all on the ground floor. You have to fill the spots one by one, up to the 100th spot on some higher floor. The garage is now degenerate. If you try to make the garage smaller, compress the matter, you can't, because all the spots are full. The only way is to build a new, higher floor, push a fermion to a higher energy state, which is very difficult. The structural integrity of the garage resisting your attempt to shrink it is analogous to degeneracy pressure. This pressure has a strange property. It depends almost entirely on the density of the matter, not on its temperature. This is because even at zero temperature, the fermions are still locked in their high energy states. This is fundamentally different from a classical gas, where the pressure drops to zero as the temperature approaches zero. A degenerate gas at absolute zero still exerts a colossal pressure. This means that an object made of degenerate matter, like a dead star, does not need to be hot to support itself against gravity. It is supported by a permanent quantum mechanical scaffolding. There are different types of degenerate matter, depending on which fermions are providing the pressure. The first and most common type is electron-degenerate matter. This is the state of matter found in the cores of stars like our Sun, and most spectacularly, in the stellar remnants known as white dwarfs. Let's follow the life of a star like our Sun. For billions of years, it fuses hydrogen into helium in its core. The outward pressure from this nuclear fusion perfectly balances the inward crush of gravity, but eventually the hydrogen fuel in the core runs out. The star begins to die. It swells into a red giant, and its core, now made of carbon and oxygen, contracts under gravity. As the core contracts, it gets incredibly dense. The carbon and oxygen atoms are stripped of their electrons, creating a soup of atomic nuclei and a sea of free electrons. The density becomes so high, hundreds of thousands of times denser than water, that the electrons are forced into a degenerate state. Their wave functions overlap, and the Pauli exclusion principle kicks in. The electrons fill up the Fermi sea, creating a powerful electron degeneracy pressure. This quantum pressure pushes outward, and eventually it becomes strong enough to halt the gravitational collapse. The star has found a new equilibrium. It has become a white dwarf. A white dwarf is an extraordinary object. It is a star with the mass of our Sun compressed into a volume the size of the Earth. A single teaspoon of white dwarf matter would weigh several tons. It is no longer generating energy through fusion. It is a stellar corpse, a glowing ember that will spend trillions of years slowly radiating away its residual heat into space, eventually becoming a cold, dark black dwarf. Its structure, its very existence, is a macroscopic demonstration of the Pauli exclusion principle. It is a star held up not by heat, but by quantum mechanics. But what if the star is much more massive than our Sun? A star with more than about 8 times the Sun's mass will have a much more dramatic death. When it runs out of fuel, its core collapses with such violence that the electron degeneracy pressure is not strong enough to stop it. The collapse is catastrophic. The core temperature and pressure skyrocket, and the electrons are crushed with such force that they are driven into the protons in a process called inverse beta decay. An electron and a proton combine to form a neutron and a neutrino. The core of the star transforms in an instant from a mixture of protons and electrons into a ball of almost pure neutrons. These neutrons are also fermions. As the collapse continues, the neutrons are squeezed together until they too become degenerate. They fill up their own Fermi sea, and they begin to exert a powerful neutron degeneracy pressure. This pressure is even stronger than the electron degeneracy pressure because neutrons are much more massive and can be packed more tightly. This neutron pressure is finally strong enough to halt the collapse, which it does with shocking abruptness. The outer layers of the star, which were still raining down on the core, slam into this newly formed incompressible ball of neutrons and rebound in a titanic explosion, a supernova. What is left behind at the center is a neutron star. This is the second type of degenerate matter, neutron degenerate matter, or neutronium. A neutron star is one of the most extreme objects in the universe. It packs the mass of 1.5 to 2 suns into a sphere just 10 to 20 kilometers, 6 to 12 miles in diameter, the size of a city. The density is beyond comprehension. A single sugar cube-sized piece of neutron star matter would weigh 100 million tons, as much as the entire human population. It is so dense that if you dropped a marshmallow on its surface, it would impact with the energy of an atomic bomb. A neutron star is a macroscopic atomic nucleus, a single entity bound together by gravity, composed almost entirely of degenerate neutrons. Like a white dwarf, it is supported against further collapse by the quantum pressure of its constituent fermions. It is another spectacular testament to the power of the Pauli exclusion principle. Degenerate matter, therefore, is the fermionic answer to the Bose-Einstein condensate. While bosons seek unity and coherence, fermions demand their personal space, and in doing so, they create a substance of incredible strength and resilience. This quantum state is not a delicate laboratory creation. It is forged in the most violent events in the cosmos, the death of stars. It is the stuff of stellar corpses, the final stable state for the vast majority of stars that will ever exist. It is a quiet but powerful reminder that the strange rules of the quantum world are not just a theory. They are written into the very fabric of the cosmos, holding up the heavens against the finality of gravitational collapse. Our exploration of degenerate matter has introduced us to the immense power of the Pauli exclusion principle, the quantum rule that forbids fermions from sharing the same state. This principle gives rise to a powerful outward pressure, a quantum scaffolding that can resist the ultimate cosmic force, gravity. Now we will examine the first and most common manifestation of this principle in the cosmos. We will journey to a stellar graveyard and explore the substance of a white dwarf, the beautiful, compact corpse of a sun-like star. A white dwarf is not just a dead star, it is a city-sized diamond, a celestial ember composed of one of the universe's most remarkable materials, electron-degenerate matter. To truly appreciate a white dwarf, we must first witness its birth, which is intertwined with the death of a star like our own Sun. For billions of years, the Sun has been in a state of perfect equilibrium. In its core, the immense pressure and temperature drive nuclear fusion, converting hydrogen into helium. The energy released by this fusion pushes outward, creating a thermal pressure that perfectly balances the relentless inward pull of the star's own gravity. The star is stable, a self-regulating nuclear furnace, but this stability cannot last forever. The fuel will eventually run out. When the Sun exhausts the hydrogen in its core in about 5 billion years, its life will enter its final dramatic phase. With the fusion engine sputtering, gravity will gain the upper hand. The core, now composed mostly of helium, will begin to contract and heat up. This heating will cause the outer layers of the Sun to expand prodigiously. The Sun will swell into a red giant, its diameter increasing 100-fold, engulfing the orbits of Mercury, Venus, and possibly even Earth. Its surface will cool, giving it a reddish hue, but its total luminosity will be far greater than it is today. While the outer layers are expanding, the core continues its collapse. The temperature and pressure in the core will eventually become so high that a new round of fusion ignites. Helium begins to fuse into carbon and oxygen. This provides a temporary reprieve, a new source of outward pressure that halts the core's collapse for a time. But helium is a far less efficient fuel than hydrogen, and it will be exhausted relatively quickly in just a few 100 million years. For a star of the Sun's mass, the temperature and pressure in the core will never become high enough to ignite the fusion of carbon and oxygen. The nuclear furnace is now extinguished for good. With no more outward pressure from fusion, gravity becomes the undisputed victor. The core, a dense ball of carbon and oxygen nuclei, begins its final, inexorable collapse. The outer layers of the red giant, no longer gravitationally bound to the contracting core, drift away into space, forming a beautiful glowing shell of gas known as a planetary nebula. At the centre of this expanding, ghostly shroud lies the exposed, collapsing core. This is the nascent white dwarf. As the core collapses, the density skyrockets. The matter becomes so compressed that the atomic structure is destroyed. The electrons are stripped from their host carbon and oxygen nuclei, a process called pressure ionization. The core becomes a strange two-component fluid, a lattice of heavy, positively charged carbon and oxygen ions, bathed in a sea of light, negatively charged, free-moving electrons. The density reaches astonishing levels, typically around 1 million grams per cubic centimetre. This means a single teaspoon of this material would weigh as much as an elephant, about 5 tons. It is at this point that the quantum rules assert themselves with spectacular force. The electrons, being fermions, are squeezed into a volume so small that their quantum wave functions overlap. They are forced into a degenerate state. As we saw in the previous chapter, they must obey the Pauli exclusion principle, filling up the available energy levels from the bottom up, creating a Fermi sea of high-energy electrons. This creates a colossal electron degeneracy pressure. This quantum pressure, which has nothing to do with temperature, pushes outward, resisting any further compression. Eventually, this electron degeneracy pressure becomes strong enough to counteract the inward pull of gravity. The collapse halts. The star settles into its final, stable and eternal configuration. It has become a white dwarf. It is a stellar remnant with a mass comparable to the Sun's, typically about 0.6 solar masses, but a volume comparable to the Earth's. It is one of the densest forms of matter in the universe. The properties of a white dwarf are dictated by this strange degenerate state. Firstly, it has a peculiar relationship between its mass and its radius. You might intuitively think that a more massive white dwarf would be larger. The opposite is true. A more massive white dwarf has a stronger gravitational pull, which compresses it more tightly. This increases the density of the electrons, which in turn increases the degeneracy pressure needed to support it. The result is that the more massive a white dwarf is, the smaller its radius. A 1.0 solar mass white dwarf is significantly smaller than a 0.6 solar mass one. This leads to a critical limit, discovered by the Indian-American astrophysicist Subrahmanyan Chandrasekhar. There is a maximum mass that a white dwarf can have. If you keep adding mass to a white dwarf, it will get smaller and denser. But the electrons can only be pushed so far. As the density increases, the electrons are forced into higher and higher energy states, and their speeds approach the speed of light. According to Einstein's theory of relativity, nothing can go faster than light, and as particles approach this speed, their behavior changes. When Chandrasekhar included the effects of special relativity in his calculations, he found that the degeneracy pressure no longer increased fast enough to counteract gravity. He calculated that if a white dwarf's mass exceeds about 1.44 times the mass of the Sun, now known as the Chandrasekhar limit, the electron degeneracy pressure will fail. Gravity will win, and the star will be doomed to collapse further, leading to a supernova or a neutron star. This discovery, for which Chandrasekhar won the Nobel Prize, is a cornerstone of stellar evolution. What is a white dwarf actually made of? Initially, it is a fluid of ions and electrons, but it is also incredibly hot, with surface temperatures that can exceed 100,000 degrees Celsius, a glowing white heat that gives it its name. As it has no source of new energy, it simply radiates its stored thermal energy into space, like a cooling ember. This cooling process is incredibly slow, taking trillions of years, far longer than the current age of the universe. As the white dwarf cools, its material is predicted to undergo one final phase transition. The carbon and oxygen ions, which have been moving freely in the electron sea, will slow down so much that the electrostatic forces between them take over. They will lock into a fixed, rigid lattice structure. The white dwarf will crystallize, starting from its core and spreading outward. The substance of the white dwarf will become a solid. But this is no ordinary solid. It is a crystal lattice of carbon and oxygen, held together by electrostatic forces and embedded in a sea of degenerate electrons. Given that carbon is the primary component, a crystallized white dwarf is, in essence, a single, Earth-sized diamond. It is the ultimate cosmic jewel, a diamond star. Astronomers have found evidence for this crystallization process in several nearby white dwarfs, including one named BPM 37093, which they have nicknamed Lucy, after the Beatles song Lucy in the Sky with Diamonds. The white dwarf, then, is the final fate for about 97% of the stars in our galaxy, including our Sun. The universe is slowly filling up with these compact, degenerate objects. They are the quiet, stable endpoint of stellar evolution for the vast majority of stars. They are a testament to the power of quantum mechanics, writ large across the cosmos. Each one is a monument, a star held in eternal stasis by the stubborn refusal of its electrons to share their quantum homes. The matter within a white dwarf is our first concrete example of a naturally occurring degenerate state. It is a bridge between the familiar world and the truly extreme. Its density is immense, but it is still composed of the familiar particles of carbon, oxygen, and electrons. It is a state of matter born from the death of a star, a final, stable configuration achieved when the fire of fusion is extinguished and the cold, hard logic of quantum mechanics takes over. It is the beautiful, crystalline corpse of a star. Having explored this city-sized diamond, our journey must now take us to an even more extreme environment, to the remnant of a much more massive star, where gravity is so strong that it overwhelms even the mighty electron degeneracy pressure, and matter is forced into an even denser and stranger state, the neutron star. We have witnessed the quiet, elegant end of a sun-like star, its core collapsing into a city-sized diamond, a white dwarf, held in eternal stasis by the quantum refusal of its electrons to be crushed further. This electron degeneracy pressure is immensely powerful, but it is not invincible. In the grand cosmic arena, there are forces of gravity so colossal that they can overwhelm this quantum defense. To witness this, we must turn to the death of a much more massive star, an event not of quiet retirement, but of cataclysmic violence. This is the story of a supernova, and of the object it leaves behind, a neutron star. In its heart, we will find our second form of degenerate matter, a substance so dense and so extreme it pushes the boundaries of known physics. This is neutron degenerate matter, often called neutronium. Our story begins with a star born with at least 8 times the mass of our Sun. A star this massive lives its life in the fast lane. Its immense gravity creates crushing pressures and scorching temperatures in its core, causing it to burn through its nuclear fuel at a prodigious rate. While the Sun will live for 10 billion years, a massive star might live for only 10 million. It forges hydrogen into helium, then helium into carbon and oxygen, just like a smaller star. But its core is so hot and dense that it doesn't stop there. It ignites a frantic sequence of further fusion stages, creating progressively heavier elements. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. The star develops a layered onion-like structure with a shell of hydrogen at the surface, followed by shells of helium, carbon, oxygen, and so on, all the way down to a core of pure iron. The creation of iron is the star's death knell. Iron is the most stable nucleus in the universe. Fusing iron into heavier elements does not release energy, it consumes energy. The star's core has become a ball of cosmic ash. The nuclear furnace is extinguished for the final time. With no outward thermal pressure to support it, The iron core, which has a mass of about 1.4 times that of our Sun, the Chandrasekhar limit, begins to collapse under its own staggering gravity. This collapse is not the gentle contraction of a white dwarf core, it is a catastrophic, runaway implosion. In less than a second, a core the size of the Earth collapses to a ball just a few dozen kilometers across. The velocity of the infalling material reaches a quarter of the speed of light. As the core implodes, the density and temperature become unimaginable. The core is initially composed of iron nuclei and a sea of degenerate electrons. The electron degeneracy pressure that supports a white dwarf fights valiantly against the collapse, but the force of gravity is simply too great. The pressure skyrockets, and the electrons are accelerated to nearly the speed of light. But it's not enough. Gravity overwhelms the electron degeneracy pressure. What happens next is a process of cosmic alchemy in reverse. The core becomes so dense that the electrons are physically forced to combine with the protons inside the iron nuclei. This process is called inverse beta decay, or electron capture. A proton, positive charge, and an electron, negative charge, merge to form a neutron, no charge, and a fleeting ghost-like particle called a neutrino. The reaction is proton plus electron arrow neutron plus neutrino. In a fraction of a second, the very nature of the matter in the core is transformed. The iron nuclei, rich in protons and electrons, are converted into a substance made almost entirely of neutrons. The core of the star has become a proto-neutron star. The neutrinos, which interact very weakly with other matter, escape in a colossal instantaneous blast, carrying away an immense amount of energy and helping to power the subsequent explosion. The collapse, however, continues. The newly formed neutrons are squeezed together with incredible force. But neutrons, like electrons and protons, are fermions. They too must obey the Pauli exclusion principle. As their wave functions overlap, they are forced into a degenerate state. Filling up their own Fermi sea, they begin to exert their own degeneracy pressure. Neutron degeneracy pressure is vastly more powerful than the electron degeneracy pressure. This is because neutrons are about 2,000 times more massive than electrons, and according to quantum mechanics, this allows them to be packed much more tightly before their quantum pressure becomes significant. The inward collapse of the core slams head-on into the unyielding wall of this newly established neutron degeneracy pressure. The collapse halts with shocking abruptness. The core, now an incompressible ball of degenerate neutrons, rebounds. This rebound creates a titanic shockwave that blasts outward through the outer layers of the star, which are still raining down on the core. The shockwave, supercharged by the energy from the escaping neutrinos, rips the star apart in a cataclysmic explosion known as a Type II supernova. For a few weeks, the single exploding star can outshine its entire host galaxy of billions of stars, blasting heavy elements forged over its lifetime far out into the cosmos, seeding the next generation of stars and planets. Left behind in the center of this expanding, beautiful chaos is the remnant of the core, a neutron star. It is one of the most extreme and fascinating objects in the universe. It is a sphere with a mass between 1.4 and about 2.2 times that of our Sun, but its diameter is only about 20 kilometers, 12 miles. It is the size of a city, but it contains more mass than our entire solar system outside the Sun. The density of a neutron star is beyond all human comprehension. A single sugar cube of neutron star matter would weigh about 100 million tons. A single drop would outweigh the Great Pyramid of Giza. This is the density of an atomic nucleus, but scaled up to a macroscopic object. A neutron star is, in a very real sense, a single, city-sized atomic nucleus, held together not by the strong nuclear force, but by gravity. The properties of a neutron star are as extreme as its density. Its surface gravity is about 200 billion times stronger than Earth's. If you could stand on its surface, you would be instantly flattened into a monatomic layer of atoms. The escape velocity is about half the speed of light. The star is also born spinning incredibly rapidly, a consequence of the conservation of angular momentum from the original, much larger star's rotation. A typical neutron star might spin several times a second, but some, known as millisecond pulsars, can spin over 700 times per second, their surfaces moving at a significant fraction of the speed of light. This rapid rotation, combined with the star's electrically conductive superfluid interior, generates the most powerful magnetic fields in the universe. A typical neutron star's magnetic field is 1 trillion times stronger than Earth's. Some, known as magnetars, have fields 1,000 times stronger still, so powerful they could wipe a credit card from halfway to the moon and would distort the electron clouds of your atoms, killing you from miles away. The matter inside a neutron star, this neutronium, is a complex and layered substance. The outer crust is thought to be a solid lattice of heavy atomic nuclei like iron in a sea of degenerate electrons, similar to a white dwarf but much denser. As one descends deeper, the pressure increases and the nuclei become more and more neutron-rich through electron capture. Eventually, a point called neutron drip is reached, where the neutrons can no longer be held within the nuclei and they drip out, forming a sea of free, degenerate neutrons. Deeper still, the nuclei dissolve completely, and the matter becomes a uniform fluid of mostly degenerate neutrons, with a small percentage of degenerate protons and electrons mixed in. This neutron-proton-electron fluid is expected to be a superfluid and a superconductor, meaning it flows with zero friction and conducts electricity with zero resistance. The heart of a neutron star is a bizarre quantum fluid, but what lies in the very center, where the pressure is most extreme? Here, we reach the frontier of modern physics. It is possible that even neutron degeneracy pressure is not the final word. Some theories predict that at these incredible densities, the neutrons themselves might break down. A neutron is not a fundamental particle. It is made of 3 smaller particles called quarks. It is possible that the core of a neutron star is a sea of deconfined quarks, a state of matter called quark matter or strange matter, which we will explore in a later chapter. The true nature of a neutron star's core is one of the biggest unsolved mysteries in astrophysics. A neutron star, this city-sized nucleus, is the second form of degenerate matter we have encountered. It is the result of gravity overwhelming the quantum defenses of electrons, only to be halted by the even more powerful quantum defenses of neutrons. It is a monument to the violence of the cosmos and the stubbornness of fermions. Each one is a laboratory for extreme physics, a place where matter is pushed to limits we can barely imagine, let alone replicate on Earth. They are the lighthouses of the cosmos, the pulsars, whose regular, sweeping beams of radiation are a constant reminder of the strange and wonderful objects that populate our universe. Having stared into the heart of this stellar remnant, we must now ask, what happens if even the mighty neutron degeneracy pressure is not enough? We have journeyed deep into the hearts of dead stars, witnessing the immense power of degeneracy pressure. We saw how the refusal of electrons to share their quantum states creates the city-sized diamond of a white dwarf, and how the even more powerful refusal of neutrons creates the ultra-dense city-sized nucleus of a neutron star. In both cases, the Pauli exclusion principle provides a quantum scaffolding that holds back the final, complete victory of gravity. But our journey into the fundamental states of matter is not yet complete. We must now push beyond the neutron itself and ask, what are the ultimate building blocks of matter, and what happens when even they are broken apart? To answer this, we must leave the stellar graveyards behind and travel to 2 even more extreme environments, the very first moments of the universe's existence and the heart of the most powerful particle colliders on Earth. In these places of unimaginable energy and temperature, we will encounter a state of matter that is both the ancestor of everything we know and a frontier of modern physics. This is the quark-gluon plasma, QGP, a primordial soup where the fundamental constituents of matter are liberated from their bonds and roam free. First, we must update our picture of the atom. We know that atoms are made of a nucleus of protons and neutrons, surrounded by a cloud of electrons. For a long time, protons and neutrons were thought to be fundamental particles. But in the 1960s, experiments involving high-energy particle collisions revealed that they have an internal structure. Protons and neutrons are each composed of 3 smaller, more fundamental particles called quarks. Quarks are one of the 2 basic types of elementary particles in the standard model of particle physics, the other being leptons, like the electron. They are truly fundamental. As far as we know, they are not made of anything smaller. There are 6 flavors of quarks, given whimsical names: up, down, charm, strange, top, and bottom. A proton is made of 2 up quarks and 1 down quark. A neutron is made of one up quark and two down quarks. These quarks are bound together inside the proton or neutron by the strongest force in nature, the strong nuclear force. This force is carried by another type of particle called a gluon. The interaction between quarks and gluons is described by a powerful theory called quantum chromodynamics, QCD. One of the most bizarre features of the strong force is a property called color confinement. Quarks have a type of charge called color charge, which has nothing to do with visible color. The force carried by the gluons is so strong that a single quark can never be found in isolation. They are permanently confined within composite particles like protons and neutrons, known collectively as hadrons. If you try to pull two quarks apart, the energy in the gluon field between them increases. This energy builds up until it is energetically cheaper to create a new quark-antiquark pair out of the vacuum. This new pair then combines with the original quarks to form two new hadrons. It's as if you tried to stretch a rubber band until it snapped, but instead of breaking, it created a new, smaller rubber band in the middle. The result is the same. You can never isolate a single end of the rubber band. You can never isolate a single quark. This is why we never see free quarks in our everyday world. They're always locked away in their proton and neutron prisons. But what if you could create an environment so hot and so dense that the very concepts of proton and neutron dissolve? Imagine heating matter to a temperature of several trillion degrees Celsius. This is a temperature more than 100,000 times hotter than the core of the Sun. At these incredible energies, the protons and neutrons would be smashed together with such violence that their boundaries would overlap and break down. The quarks and gluons inside them would no longer be confined to their individual hadrons. They would be deconfined, free to move about in a much larger volume. This is the quark-gluon plasma. It is a state of matter where quarks and gluons, the fundamental building blocks of atomic nuclei, are liberated from their confinement and exist as a collective, interacting soup. It is a thermalized, dense state of deconfined partons, a general term for quarks and gluons. This state of matter is believed to have existed for the first few microseconds, millionths of a second, after the Big Bang. In that primordial moment, the universe was an incredibly hot, dense fireball of QGP. As the universe expanded and cooled, it went through a phase transition, and the free quarks and gluons froze out, condensing into the protons and neutrons that make up all the matter in the universe today. The protons and neutrons we see are, in a sense, fossilized droplets from that primordial quark-gluon ocean. For decades, the QGP was purely a theoretical prediction of QCD. But physicists are experimentalists at heart. They wanted to create and study this primordial state of matter in the laboratory. To do this, they needed to recreate the conditions of the early universe, if only for a fleeting instant in a microscopic volume. This requires particle accelerators, colossal machines that use powerful electromagnetic fields to accelerate heavy atomic nuclei to near the speed of light. At facilities like the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory in the US, and the Large Hadron Collider, LHC, at CERN in Switzerland, scientists accelerate beams of heavy nuclei, like gold or lead, in opposite directions around a circular track. At designated points, they steer the beams into a head-on collision. When two gold nuclei, each containing 197 protons and neutrons, collide at 99.99% the speed of light, the energy released in the microscopic collision zone is immense. For a brief moment, a fireball is created with a temperature of over 4 trillion degrees Celsius, momentarily recreating the conditions of the microsecond-old universe. By analyzing the torrent of particles that fly out from this collision, scientists can deduce the properties of what was created in the middle. And the evidence is clear. For a fraction of a second, about 10 to the minus 23 seconds, they are creating a tiny droplet of quark-gluon plasma. They have successfully melted the proton and neutron. What have they learned about this strange primordial soup? One of the biggest surprises was its behavior. Initially, theorists expected the QGP to behave like a gas. Since the quarks and gluons were deconfined and at very high energy, it was thought they would interact only weakly, flying around like particles in a hot gas. The experiments showed the exact opposite. The QGP behaves not like a gas, but like an almost perfect liquid. A perfect liquid is one that has extremely low viscosity, a measure of its resistance to flow. The QGP created at RHIC and the LHC has a viscosity close to the lowest value theoretically allowed by the laws of quantum mechanics. This means the quarks and gluons, even though they are deconfined, are still interacting very strongly with each other. They flow together in a highly coordinated collective manner, like a school of fish rather than a swarm of bees. This discovery has forced a major revision of the theoretical models of the QGP, and has opened up fascinating connections to other areas of physics, such as string theory and the physics of black holes, which have also been used to describe strongly coupled fluids. The study of the QGP is a journey back to the origin of mass itself. Most of the mass of the protons and neutrons that make up our bodies does not come from the mass of the quarks within them. The up and down quarks are actually very light. Instead, about 99% of the mass of ordinary matter comes from the kinetic energy of the quarks and the binding energy of the gluon field that holds them together, as described by Einstein's famous equation E equals mc squared. In the QGP, where the quarks are deconfined, they revert to their much lighter, bare masses. So, by creating QGP, scientists are studying the very mechanism by which the mass of the visible universe was generated as the universe cooled. The quark-gluon plasma represents a new frontier in our understanding of matter. It is a state that exists at the opposite extreme from the Bose-Einstein condensate. The BEC is created at the lowest possible energies, where quantum coherence dominates. The QGP is created at the highest achievable energies, where the very structure of nuclear matter dissolves. It is the primordial ancestor of all the nuclei in the universe. It is a perfect liquid forged in the fire of the Big Bang and recreated in miniature on Earth. It reminds us that the familiar particles we take for granted, protons and neutrons, are themselves just composite structures, vessels that have confined the true fundamental particles of matter ever since the universe was just a few microseconds old. Our journey has taken us beyond the atom, beyond the nucleus, and into the fundamental soup of creation itself. Our journey has taken us deep into the heart of matter, from the familiar states of our world to the exotic plasmas of stars, the quantum coherence of condensates, and the primordial soup of the Big Bang. We have seen that protons and neutrons, the building blocks of atomic nuclei, are themselves composed of smaller particles called up and down quarks. But the universe, in its boundless creativity, has more flavors of quarks to offer. Two of these, the charm and top quarks, are incredibly massive and unstable, decaying in a fraction of a second. The bottom quark is similarly short-lived, but the third flavor, the strange quark, is a character of special interest. It is heavier than the up and down quarks, but not so heavy that it is impossible to create and study. The existence of this third, relatively accessible quark leads to one of the most tantalizing and unsettling possibilities in all of physics, the hypothesis of strange matter. This is a journey into a purely theoretical realm, a state of matter that may or may not exist, but whose properties, if it does exist, would be revolutionary. Strange matter could be the true ground state, the most stable form of all matter in the universe, and if it can exist in small, stable nuggets, these strangelets would be one of the most bizarre and potentially dangerous substances imaginable. The story begins back in the core of a neutron star. We established that a neutron star is a city-sized ball of degenerate neutrons, supported by neutron degeneracy pressure. But we also hinted that in the extreme pressures of the star's core, the neutrons themselves might be crushed so tightly that they dissolve into their constituent up and down quarks, forming a sea of quark matter. Physicists Arnold Bodmer and Edward Witten took this idea a step further in the 1970s and 80s. They asked, what would happen if some of the up and down quarks in this dense quark soup were converted into strange quarks? According to the rules of quantum mechanics and the Pauli exclusion principle, a system is most stable when its particles can occupy the lowest possible energy states. In a dense soup of only up and down quarks, the Fermi seas for these two types of quarks would be filled up to a very high energy level. But if some of the high energy up and down quarks could transform into strange quarks, a process allowed by the weak nuclear force, they could settle into the lower energy rungs of this strange quark energy ladder. It's like having 3 parking garages, up, down, and strange, instead of just 2. By distributing the cars among 3 garages, the highest filled spot in any one garage will be lower than if you only had 2. This means that a mixture of up, down, and strange quarks might have a lower total energy and therefore be more stable than a mixture of just up and down quarks. This hypothetical stable configuration of roughly equal numbers of up, down, and strange quarks is what is known as strange quark matter, or simply strange matter. This leads to a mind-bending hypothesis, the strange matter hypothesis. It proposes that strange matter is not just more stable than ordinary quark matter, but that it might be more stable than ordinary nuclear matter, protons and neutrons as well. If this is true, it would mean that the protons and neutrons that make up our entire world, our bodies, the Earth, the Sun, are not the true ground state of matter. They are merely in a long-lived, but ultimately unstable, metastable state, like a ball resting in a small dip on the side of a large hill. Strange matter would be the true valley floor, the state of absolute stability. If this hypothesis is correct, then the cores of neutron stars might not be made of neutrons at all. They might have converted into massive stable balls of strange matter. Such a star would be called a quark star or a strange star. It would be even denser and smaller than a neutron star, as the quarks can be packed more tightly than neutrons. Distinguishing a strange star from a neutron star through astronomical observation is incredibly difficult, but it is an active area of research. The detection of a star that is too small and dense to be a neutron star would be powerful evidence for the existence of strange matter. The strange matter hypothesis has an even more startling and dramatic implication. The strong force that confines quarks inside protons and neutrons is short range. But what if a lump of strange matter could exist outside the immense gravitational pressure of a neutron star? If strange matter is truly the ground state of matter, then it should be stable even at zero pressure. A hypothetical, stable, microscopic lump of strange matter is called a strangelet. A strangelet would be an entirely new kind of object. It would be a quark nugget, a single giant hadron composed of billions or trillions of up, down, and strange quarks, all bound together by the strong force. It would be in essence a single, massive nucleus, but one containing strange quarks. It would be electrically neutral, or very nearly so, incredibly dense and stable. The truly bizarre and frightening property of a strangelet arises from its proposed stability. If a strangelet were to come into contact with a piece of ordinary matter, such as the nucleus of an atom, it would begin to convert that ordinary matter into more strange matter. The strangelet would absorb the nucleus, and the up and down quarks from the nucleus's protons and neutrons would be assimilated into the strangelet's quark soup, with some of them converting to strange quarks to maintain the low-energy balance. The process would release energy, and the strangelet would grow. This conversion process would be catalytic. The strangelet would be like a seed crystal dropped into a supersaturated solution, causing the entire solution to crystallize. Or, in a more famous analogy, it would be like the ice nine from Kurt Vonnegut's novel Cat's Cradle, a form of ice that is stable at room temperature and instantly freezes any water it touches. A strangelet would eat the nuclei of ordinary matter, turning them into more strange matter and growing larger in the process. This leads to a chilling doomsday scenario. What if a tiny, stable strangelet were to strike the Earth? It would pass through the atmosphere and the crust, and upon encountering the dense matter of the Earth's interior, it would begin the conversion process. It would start consuming the Earth's core, converting it, nucleus by nucleus, into a growing ball of hot, dense, strange matter. The process would be unstoppable, an exotic chain reaction that would, in a relatively short amount of time, convert the entire planet into a single, hot, planet-sized sphere of strange matter. This Ice 9 scenario has led to serious safety reviews for particle accelerator experiments like RHIC and the LHC. These colliders are designed to create tiny fireballs of quark-gluon plasma. Could such an experiment accidentally create a small, stable, negatively charged strangelet that could then start converting the detector and then the rest of the world? The consensus from extensive safety studies is that this is virtually impossible. Firstly, the collisions create incredibly high temperatures, which would favour the creation of many different particle-antiparticle pairs, not the cold, stable configuration of a strangelet. Secondly, even if a strangelet were formed, the chances of it being stable and having the right properties, like a negative charge to attract nuclei, are considered infinitesimally small. Most importantly, nature has already been running a much higher energy version of these experiments for billions of years. The Earth and the Moon are constantly being bombarded by high-energy cosmic rays, with energies far exceeding anything we can create in a collider. The fact that the Moon is still there, and has not been converted into a ball of strange matter, is considered the strongest evidence that stable, dangerous strangelets are not easily formed. So, are strangelets real? It's possible that tiny strangelets are a component of dark matter, flying harmlessly through the cosmos. There have been a few unconfirmed reports of cosmic ray detectors registering events that could be interpreted as the passage of a strangelet. However, the evidence is far from conclusive. The concept of strange matter remains one of the most fascinating and speculative ideas in modern physics. It is a direct consequence of the existence of the 6 flavors of quarks and the fundamental rules of quantum chromodynamics. It suggests that the very ground beneath our feet might be in a state of cosmic precarity, a metastable configuration waiting for a nudge to fall into a more stable state. It forces us to confront the possibility that the universe could harbour forms of matter with properties far beyond our normal experience. Whether strange matter is real or not, its story is a powerful illustration of the scientific process. It is a hypothesis born from fundamental theory, with testable, though difficult, predictions. It pushes us to search for quark stars, to analyse cosmic rays, and to think deeply about the safety of our most ambitious experiments. It is a journey to the ultimate limits of density and stability, a theoretical squeeze that goes beyond even the neutron into the fundamental heart of matter itself. It is a reminder that in the calm cosmos, there may yet be forms of matter stranger and more powerful than we can possibly imagine. Our journey through the strange states of matter has so far been a story of the visible. We have explored matter forged in stars, crushed in stellar corpses, and created in the fire of the Big Bang. All of it, plasma, degenerate matter, quark-gluon plasma, is what physicists call baryonic matter. It is matter made of baryons like protons and neutrons and their constituent quarks. It is the stuff that interacts with light, the stuff we can see, touch, and study. It is the substance of us, our planet, and every star that shines in the night sky. But now our journey must take a turn into the shadows, into the unseen. We're about to confront one of the most profound and humbling mysteries in all of science, the fact that everything we can see, everything we have studied so far, makes up only a tiny fraction of the matter in the universe. The vast majority of matter is something else entirely. It is a cosmic ghost, an invisible substance that does not shine, reflect, or interact with light in any way. We know it only by its gravitational embrace. This is the story of dark matter. The first hints of this cosmic mystery came in the 1930s, long before the idea was taken seriously. A Swiss-American astronomer named Fritz Zwicky was studying the Coma Cluster, a massive conglomeration of over 1,000 galaxies. He was measuring the velocities of the individual galaxies within the cluster as they orbited their common centre of mass. He used these velocities to calculate the total mass of the cluster required to hold it all together gravitationally. If the cluster didn't have enough mass, the fast-moving galaxies would simply fly off into space. Then, he calculated the cluster's mass in a different way, by adding up all the light from all the stars in all the galaxies. This gave him an estimate of the mass of the visible baryonic matter. The result was a stunning discrepancy. The mass required to hold the cluster together was hundreds of times greater than the mass he could see. Zwicky concluded that the vast majority of the matter in the cluster must be some form of dunkel materie, or dark matter. His observation was largely ignored for decades, dismissed as a curiosity or an error. The idea was resurrected in the 1970s by the meticulous work of American astronomer Vera Rubin. She was studying the rotation of individual spiral galaxies, like our own Milky Way. According to our understanding of gravity, the stars in the outer parts of a galaxy should orbit more slowly than the stars in the inner parts, just as the outer planets in our solar system, like Neptune, orbit the Sun much more slowly than the inner planets, like Mercury. This is because most of the visible mass, the stars and gas, is concentrated in the central bulge of the galaxy. But this is not what Rubin found. She measured the orbital speeds of stars and gas clouds at various distances from the galactic centre and discovered that the stars in the outer regions were moving just as fast as the stars in the inner regions. The galaxy rotation curves, as they are called, were flat. There was only one possible explanation. The galaxies had to contain a huge amount of unseen mass, extending far beyond the visible disk of stars. This mass had to be distributed in a vast spherical halo surrounding the entire galaxy. The fast-moving outer stars were being held in their orbits by the gravitational pull of this invisible halo. The visible galaxy was like a tiny luminous jewel embedded in a colossal invisible sphere of dark matter. Rubin's work provided undeniable evidence that Zwicky had been right. The problem wasn't just in galaxy clusters, it was in every galaxy. The universe was missing most of its matter. Since then, the evidence for dark matter has become overwhelming, coming from many independent lines of inquiry. One of the most powerful is gravitational lensing. According to Einstein's theory of general relativity, mass warps the fabric of space-time. A large concentration of mass, like a galaxy cluster, can act as a giant cosmic lens, bending the path of light from more distant objects as it passes by. By observing how the images of distant galaxies are distorted and magnified by a foreground cluster, astronomers can create a map of the mass distribution in that cluster. These maps consistently show that the vast majority of the mass is not where the visible galaxies are. It is distributed in a large, smooth halo of invisible dark matter, which contains far more mass than all the stars and gas combined. In some cases, like the famous Bullet cluster, a collision between two galaxy clusters has physically separated the hot, glowing gas, ordinary, matter from the dark matter, allowing us to see the two components independently. The lensing map shows the masses with the invisible dark matter, not with the visible gas. The cosmic microwave background, the faint afterglow of the Big Bang, provides another crucial piece of evidence. The tiny temperature fluctuations in the CMB are the seeds from which all cosmic structures, like galaxies and clusters, grew. The precise pattern of these fluctuations depends sensitively on the composition of the early universe. When astronomers analyze the CMB data from satellites like WMAP and Planck, their models only fit the data if the universe contains about 5 to 6 times more dark matter than ordinary baryonic matter. So what is this cosmic ghost? This is the central question. We know what dark matter is not. It is not just ordinary matter that is dark, like cold gas, dust, or dead stars, collectively known as MACHOS, for massive astrophysical compact halo objects. Extensive searches for such objects have shown that they cannot account for more than a tiny fraction of the missing mass. Dark matter must be something fundamentally new. It must be a new type of particle, one that is not part of the standard model of particle physics. This hypothetical particle must have specific properties. It must be dark, meaning it does not interact with the electromagnetic force. It doesn't emit, absorb, or reflect light. It must be cold, meaning it was moving slowly in the early universe. This is necessary for it to clump together to form the halos that seed galaxy formation. And it must be stable, having survived from the Big Bang to the present day. Physicists refer to this generic class of particles as WIMPs, which stands for weakly interacting massive particles. Weakly interacting means that, in addition to gravity, they might interact via the weak nuclear force, the same force responsible for certain types of radioactive decay. Massive means they have a significant mass, perhaps 10 to 1,000 times the mass of a proton. The idea is that these particles were created in huge numbers in the hot, dense conditions of the early Big Bang. As the universe expanded and cooled, they froze out, leaving a relic abundance that perfectly matches the amount of dark matter we observe today. This coincidence is often called the WIMP miracle. Many theories of physics beyond the standard model, such as supersymmetry, naturally predict the existence of particles with exactly these properties. Supersymmetry proposes that every known particle has a heavier superpartner. The lightest of these superpartners, often called the neutralino, is a perfect WIMP candidate. It's massive, stable, and interacts weakly. The hunt for the WIMP particle is one of the most intense and exciting efforts in modern science, proceeding along 3 main fronts. The first is direct detection. Deep underground, shielded from the cosmic rays that constantly bombard the Earth's surface, physicists have built incredibly sensitive detectors. These experiments, like Lux Zeppelin in the US, Xenont in Italy, and Pandex in China, are essentially looking for the incredibly rare event of a dark matter particle from the galaxy's halo flying through the Earth and happening to bump into an atomic nucleus in their detector. Such a collision would produce a tiny, almost imperceptible flash of light or vibration, which the detectors are designed to pick up. So far, despite years of searching and increasing sensitivity, no definitive signal has been found. The second front is indirect detection. If dark matter particles are WIMPs, they should occasionally collide with each other in regions of high dark matter density, like the centre of our galaxy or the Sun. When they collide, they should annihilate, producing a shower of ordinary detectable particles like high-energy gamma rays, neutrinos, or antimatter. Telescopes like the Fermi Gamma Ray Space Telescope and neutrino detectors like IceCube at the South Pole are searching for such an annihilation signal. There have been some tantalizing hints, but again, no smoking gun discovery. The third front is production. If we can't find dark matter in space, perhaps we can create it on Earth. At the Large Hadron Collider, physicists collide protons at enormous energies to recreate the conditions of the early universe. The hope is that some of these collisions will produce dark matter particles. Since the particles themselves are invisible, they can't be detected directly. Instead, physicists look for their signature, missing energy. If a collision produces particles that fly off in one direction, but there is no corresponding recoil in the other direction, it implies that some invisible particles must have been created and carried away momentum and energy without being detected. So far, the LHC has not seen any unambiguous evidence for dark matter production. The lack of a definitive discovery has led some physicists to consider other possibilities. Perhaps dark matter is not a WIMP, but a much lighter particle called an axion. Or perhaps it interacts with ordinary matter through a new, undiscovered dark force. A more radical idea is that dark matter doesn't exist at all, and that our theory of gravity is wrong. Theories like modified Newtonian dynamics, MOND, propose that gravity behaves differently on galactic scales, eliminating the need for dark matter. However, these theories have struggled to explain the full range of evidence, particularly from gravitational lensing and the cosmic microwave background. For now, dark matter remains a profound enigma. It is a state of matter whose existence is undeniable, but whose identity is completely unknown. It is the invisible scaffolding upon which our visible universe is built. It dictates the structure of galaxies, the dynamics of clusters, and the ultimate fate of the cosmos. It is a constant, humbling reminder that our senses, and even our most powerful instruments, only reveal a tiny sliver of reality. The universe we see is just the foam on the surface of a deep, dark, and mysterious ocean. The quest to identify this cosmic ghost, to give a name and a face to the darkness, is one of the great scientific adventures of our time. We have just confronted the humbling reality of dark matter, the invisible substance that makes up the vast majority of the universe's mass and holds our galaxies together. It is a profound mystery, a cosmic ghost whose gravitational presence is undeniable, but whose identity remains unknown. But the cosmos it turns in holds an even deeper, more perplexing secret. As if an invisible form of matter weren't enough, the universe is also dominated by an invisible form of energy, a mysterious force that is actively working against gravity, pushing the very fabric of space-time apart and accelerating the expansion of the universe. This is the story of dark energy. It is, without a doubt, the single greatest mystery in all of physics, a discovery that has shaken our understanding of the cosmos to its very core, and has revealed that the ultimate fate of the universe is far stranger than we ever imagined. The story of dark energy begins with the story of the universe's expansion. In the 1920s, astronomer Edwin Hubble made a landmark discovery. By observing distant galaxies, he noticed that almost all of them were moving away from us. More importantly, he found that the farther away a galaxy was, the faster it was receding. This observation, now known as Hubble's law, was the first direct evidence that the universe is not static. It is expanding. The galaxies are not flying away from us through space. Rather, the space between the galaxies is itself stretching, carrying the galaxies along with it like raisins in an expanding loaf of bread. This discovery painted a new picture of the cosmos, one with a history and a future. If the universe is expanding now, it must have been smaller, denser, and hotter in the past. This led directly to the Big Bang theory, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. For the rest of the 20th century, the central question in cosmology was about the future of this expansion. The universe is filled with matter, both ordinary and dark, and matter has gravity. Gravity pulls things together. Therefore, the mutual gravitational attraction of all the matter in the universe should be acting as a brake on the expansion, slowing it down over time. The ultimate fate of the universe depended on a simple competition between the outward momentum of the expansion and the inward pull of gravity. There were two main possibilities. If there was enough matter in the universe, its gravitational pull would eventually be strong enough to halt the expansion and reverse it. The universe would begin to contract, heading for a big crunch, a final, fiery collapse. If there wasn't enough matter, gravity would slow the expansion, but never quite stop it. The universe would continue to expand forever, but at an ever-decreasing rate, heading for a cold, dark, and empty future often called the Big Freeze. The goal of cosmologists was to measure the cosmic deceleration, the rate at which the expansion was slowing down, to determine which of these fates awaited us. In the late 1990s, two independent teams of astronomers set out to do just that. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. They used a specific type of stellar explosion, a type Ia supernova, as a standard candle to measure cosmic distances. A type Ia supernova occurs when a white dwarf star in a binary system pulls matter from its companion, exceeds the 1.44 solar mass Chandrasekhar limit, and explodes in a thermonuclear detonation. Because they all explode at the same mass, they all have nearly the same intrinsic brightness. This is incredibly useful. If you know how bright something truly is, you can determine how far away it is by measuring how dim it appears. By finding these supernovae in distant galaxies, the teams could measure their distance with great precision. They could also measure how fast the galaxies were receding by looking at their redshift, the stretching of their light due to the expansion of space. By plotting the distance versus the redshift for many supernovae at different distances, they could map out the history of the universe's expansion. They expected to see that the expansion was faster in the past and is slower now. They expected to measure the deceleration. What they found was the complete opposite. The most distant supernovae were dimmer than they were supposed to be. This meant they were farther away than their redshifts would suggest. The only way for this to be true was if the expansion of the universe had not been slowing down, but had been speeding up over the last several billion years. Both teams, to their astonishment, came to the same inescapable conclusion. The expansion of the universe is accelerating. This discovery, which earned Perlmutter, Schmidt and Rees the 2011 Nobel Prize in Physics, was a bombshell. It turned cosmology on its head. An accelerating expansion meant that the universe was not being dominated by the attractive force of gravity from matter. Instead, it had to be dominated by some new, unknown component with a bizarre and powerful property, a repulsive gravitational effect. This mysterious anti-gravitational substance was given the name dark energy. What is this dark energy? The honest answer is, we don't know. It is a complete mystery, but we can describe its properties. Unlike matter, which clumps together under gravity to form galaxies and clusters, dark energy appears to be smooth and uniformly distributed throughout space. And unlike matter, whose gravitational pull weakens as the universe expands and the matter becomes more dilute, the effect of dark energy seems to be constant or nearly constant. The leading theoretical candidate for dark energy is a concept that Albert Einstein himself proposed and later abandoned, calling it his biggest blunder. It is the cosmological constant, represented by the Greek letter lambda, LA-B-D-A. When Einstein was developing his theory of general relativity, the prevailing view was that the universe was static, but his equations showed that a universe filled with matter should collapse under its own gravity. To counteract this, he added an extra term to his equations, the cosmological constant, which represented a form of energy inherent to the fabric of space-time itself, a kind of vacuum energy that would create a repulsive force to hold the universe up. When Hubble discovered the universe was expanding, Einstein happily discarded the term. Now it has returned with a vengeance. A cosmological constant behaves exactly like the dark energy we observe. It is an intrinsic energy of the vacuum of space. As space expands, more space is created, and thus more vacuum energy is created, which in turn causes space to expand even faster. This creates a runaway, accelerating expansion. According to this idea, even in a perfectly empty universe, the vacuum itself would possess a non-zero energy that drives cosmic acceleration. The problem with this idea is a massive one, often called the cosmological constant problem, or the vacuum catastrophe. When physicists use quantum field theory to try and calculate how much energy the vacuum should have, based on the virtual particles that constantly pop in and out of existence, they get a number that is absurdly large. It is about 10 to the power of 120, a 1 followed by 120 zeros, times larger than the amount of dark energy we actually observe. This is by far the worst theoretical prediction in the history of physics. It is a profound disagreement between our theories of the very small, quantum mechanics, and the very large, general relativity, and it suggests we are missing something fundamental in our understanding of physics. Because of this problem, other theories have been proposed. Perhaps dark energy is not a constant, but a new dynamic field that fills all of space, which has been nicknamed quintessence. Unlike the cosmological constant, the energy density of this field could change over time and space. Or perhaps the acceleration is a sign that Einstein's theory of general relativity itself needs to be modified on cosmic scales, just as Newton's theory of gravity needed to be modified. Whatever dark energy is, its discovery has painted a new and startling portrait of our universe. According to the latest measurements from the Planck satellite, the cosmic budget is as follows. All the ordinary baryonic matter we have ever known, stars, planets, gas, yes, makes up a mere 4.9% of the total energy density of the universe. Dark matter, the invisible scaffolding of galaxies, makes up 26.8%. The rest, a whopping 68.3%, is dark energy. We live in a universe where the familiar matter we see is just a tiny bit of cosmic froth on the surface of a vast dark ocean, and the ocean itself is being driven apart by a mysterious repulsive force. The existence of dark energy also dictates the ultimate fate of the universe. Because the dark energy density remains constant as space expands, its influence grows over time, while the influence of matter and dark matter diminishes as they become more dilute. We are living in the era where dark energy has just taken over as the dominant component of the cosmos. The acceleration has begun, and it will continue. This leads to a strange and lonely future. As the expansion accelerates, all the galaxies that are not gravitationally bound to our own local group will eventually be pushed away from us faster than the speed of light. This doesn't violate relativity, as it is the space between us that is stretching. Their light will be redshifted into oblivion, and they will disappear from our view. The sky, in the far distant future, will become a dark and empty place, containing only the stars of our own Milky galaxy, the merged galaxy of the Milky Way and Andromeda. Future astronomers in this lonely island universe will have no way of knowing that other galaxies ever existed, or that the universe was ever expanding. They will live in what appears to be a static, empty cosmos. Eventually, over trillions of years, the stars in our own galaxy will burn out, leaving behind a graveyard of black dwarfs, neutron stars, and black holes. The universe will enter a dark era, a cold, quiet, and ever-expanding void. This scenario is often called the Big Freeze or heat death. If dark energy is even stranger than we think, a hypothetical form called phantom energy that grows stronger over time, the future could be even more dramatic. In a Big Rip scenario, the repulsive force of dark energy would eventually become so strong that it would overcome not just the gravity between galaxies, but the gravity holding galaxies together, then solar systems, and eventually it would become strong enough to overcome the electromagnetic and nuclear forces, tearing apart stars, planets, and even atoms themselves, ripping the very fabric of reality to shreds. Dark energy is the deepest mystery of our time. It is a fundamental property of our universe that we have only just discovered, and it has completely reshaped our cosmic narrative. It tells us that we are living in a special time. The brief epoch after matter has built the beautiful structures we see, but before an unknown force drives them all apart into an endless, accelerating darkness. The quest to understand the nature of this cosmic anti-gravity is the driving force of modern cosmology, a search for an answer that will undoubtedly lead to a new revolution in our understanding of space, time, and the ultimate fate of our calm and yet accelerating cosmos. Our cosmic journey has taken us to the extremes of temperature and density, from the primordial fire of the quark-gluon plasma to the crushing gravity of a neutron star. We have confronted the vast invisible mysteries of dark matter and dark energy. Now we return to the realm of the ultra-cold, the world near absolute zero where quantum mechanics takes center stage. We have already met the Bose-Einstein condensate, a state where a dilute gas of atoms unifies into a single quantum wave. But nature first revealed its macroscopic quantum magic not in a gas, but in a liquid. This chapter is about that liquid, a substance that defies common sense and appears to break the laws of friction. It is a liquid that can flow up walls, squeeze through impossibly small cracks, and remain in motion forever. This is the story of the superfluid, a quantum state of matter that turns a simple liquid into a universe in a drop. The story of superfluidity is the story of helium, the second simplest and second most abundant element in the universe. On Earth, helium is best known as the light, inert gas used to fill party balloons. But when cooled down to just 4.2 Kelvin, minus 269 degrees Celsius, helium gas condenses into a clear, colourless liquid. This liquid helium-4, so-called because its nucleus contains 2 protons and 2 neutrons, behaves, at first, like a normal liquid. It boils, it has viscosity, and it sits in a container just as you would expect. But as you continue to cool this liquid helium, something extraordinary happens. At precisely 2.17 Kelvin, a temperature known as the lambda point, named for the lambda shape of its specific heat graph, the liquid undergoes a dramatic phase transition. The vigorous boiling suddenly ceases. The liquid becomes perfectly still, calm and clear. It has transformed into a new state known as helium-2. This placid appearance, however, hides a world of bizarre and seemingly impossible behaviour. The liquid has become a superfluid. What is a superfluid? It is a fluid that flows with exactly zero viscosity. Viscosity is a measure of a fluid's internal friction. Honey is highly viscous. It resists flow. Water is less viscous. A superfluid has no resistance to flow at all. If you were to set a superfluid swirling in a circular container, it would, in principle, continue to swirl forever, never slowing down. There is no friction between its constituent atoms to dissipate the motion as heat. This single property, zero viscosity, gives rise to a host of astonishing behaviours that seem to defy gravity and logic. One of the most famous is the creeping film. If you place an empty beaker inside a bath of superfluid helium, a thin, almost invisible film of the superfluid will spontaneously crawl up the outside of the beaker, over the lip, and down the inside, until the level of the liquid inside the beaker is the same as the level outside. If you then lift the beaker partially out of the bath, the film will reverse its course, crawling up the inside of the beaker and down the outside, dripping back into the bath until the beaker is empty. The fluid appears to be actively defying gravity, driven by a relentless urge to find the lowest possible energy level. Another famous demonstration is the fountain effect. If a tube packed with a fine powder, to create very narrow channels, is placed in a bath of superfluid and then gently heated, for example by shining a light on it, the superfluid will shoot up out of the top of the tube in a spectacular fountain. The heat creates a temperature gradient, and the superfluid component is driven with incredible force toward the warmer region. Perhaps the most telling property is its ability to leak through impossibly small cracks. A normal liquid is held in a container because its atoms are too large to pass through the microscopic pores of the material. But a superfluid can leak through superleaks, cracks so small that even helium gas cannot pass through them. It seems to flow through solid matter as if it were a ghost. How can a liquid behave in such a bizarre way? The answer, once again, lies in the quantum world. A helium-4 atom with its 2 protons, 2 neutrons and 2 electrons has an overall integer spin. This means it is a boson. As we cool the liquid helium below the lambda point, the helium atoms undergo a Bose-Einstein condensation. Just like the atoms in the dilute gas BEC we discussed earlier, the helium atoms begin to fall into the single lowest energy quantum state. They lose their individual identities and begin to behave as a single, massive, coherent quantum entity. The entire liquid is now described by a single wave function. This is the key to understanding its strange properties. The liquid is essentially a mixture of two interpenetrating fluids, a normal fluid component, made of the few atoms that are still in excited higher energy states, and a superfluid component, made of the vast majority of atoms that have condensed into the ground state. The normal fluid has viscosity and behaves like a regular liquid. The superfluid component has zero viscosity. As you cool the liquid from the lambda point down toward absolute zero, the proportion of the superfluid component increases until, at absolute zero, the entire liquid would be a pure superfluid. The zero viscosity of the superfluid component can be understood through quantum mechanics. In a normal fluid, flow is dissipated by atoms colliding with each other and with the walls of the container, creating random thermal excitations. But in the superfluid, all the atoms are already in the single lowest possible energy state. There are no lower energy states for them to fall into to create friction. To slow down the collective flow, you would have to excite an atom out of the condensate into a higher energy state, which requires a minimum amount of energy, known as the energy gap. Below a certain critical velocity, there isn't enough energy in the flow to create these excitations. Therefore, the flow is perfectly frictionless. It is a quantum state of motion for the entire liquid. The creeping film is a result of this frictionless flow. The thin film of helium that coats all surfaces is pulled up the walls of the beaker by the weak van der Waals forces between the helium and the wall. In a normal liquid, this upward creep would be immediately halted by friction, but in a superfluid, there is no friction to stop it. The film flows effortlessly upward and over the edge. The ability to leak through superleaks is also a direct consequence of its quantum nature. The liquid is not flowing through the cracks as a collection of individual atoms, but as a single, coherent matter wave. The wave can tunnel through energy barriers that would be insurmountable for a classical particle, allowing the fluid to pass through microscopic pores. One of the most fascinating properties of a superfluid is its response to rotation. If you try to spin a bucket of normal water, the water will eventually spin along with the bucket due to friction, but you cannot spin a superfluid in the same way. Because it is a single quantum wave, it can only rotate in discrete quantized units. If you spin a container of superfluid helium, the superfluid component will initially remain perfectly still. As you increase the speed of rotation, the superfluid will suddenly form tiny, stable whirlpools called quantized vortices. Each vortex is a microscopic tornado with a core that is just one atom wide, and the circulation of the fluid around each vortex is precisely quantized. It can only be an integer multiple of a fundamental constant, Planck's constant divided by the mass of a helium atom. The superfluid can only rotate by creating an array of these identical perfect quantum whirlpools. Looking at these vortex lattices is like looking directly at the granular, quantized nature of the quantum world, scaled up to a macroscopic level. So, superfluidity is a macroscopic window into the quantum realm. It's a state of matter where the bizarre rules of quantum mechanics, usually hidden at the subatomic level, manifest themselves in the visible, tangible behavior of a liquid. What about helium-3, the lighter isotope of helium with 2 protons but only 1 neutron? A helium-3 atom has a half-integer spin, which means it is a fermion. According to the rules, fermions cannot share a quantum state, and therefore should not be able to form a Bose-Einstein condensate or a superfluid. For a long time, this was the accepted wisdom. But in the 1970s, physicists discovered that if you cool liquid helium-3 to incredibly low temperatures, just a few thousandths of a degree above absolute zero, it also becomes a superfluid. The mechanism is a beautiful quantum dance, analogous to what happens with electrons in a superconductor. The helium-3 atoms, which are fermions, feel a very weak residual attraction to each other. At these ultra-low temperatures, this weak attraction is enough to bind them together into pairs. Each pair of fermions acts as a single entity, and since the pair has an integer spin, it behaves like a boson. These Cooper pairs of helium-3 atoms can then undergo a Bose-Einstein condensation, forming a superfluid. The superfluidity of helium-3 is even more complex and richer than that of helium-4, with multiple different superfluid phases, and its discovery earned the 2003 Nobel Prize in Physics. Superfluidity is more than just a laboratory curiosity. It is a fundamental state of matter that provides a clean, controllable system for studying the laws of quantum mechanics on a large scale. Theorists believe that the neutronium in the core of a neutron star is also a superfluid. The behavior of this stellar superfluid is thought to be responsible for the sudden spin-ups, or glitches, that are occasionally observed in the rotation of pulsars. The study of superfluids on Earth can therefore give us insights into the behavior of matter in some of the most extreme environments in the cosmos. In a drop of superfluid helium, we find a universe of quantum wonders. It is a place where friction vanishes, where liquids climb walls, and where rotation happens in discrete perfect steps. It is a powerful demonstration that the world is fundamentally quantum, and that under the right conditions of extreme cold, this hidden nature can emerge in spectacular and beautiful ways. It is a calm, quiet liquid that contains the turbulent quantized heart of the cosmos.